Welcome! In this series of videos, we will cover the design and implementation of a project, from initial design, through coding and development to testing, using the PowerBasic Windows and Console compilers. Today, we will amend our application to create blockchain records for transactions. In this project, there are currently 5 computers. Octo002 is running the monitoring application, and is just used to allow us to watch what the other computers are actually doing. The remaining 4 computers are communicating with each other and carrying out transactions using UDP, the User Datagram Protocol. We covered how all this works in the previous videos. What we're going to do today is to record these transactions in a blockchain. Think of each block as being a parcel of data. Block 0 is the genesis block and is hard-coded into the system. For this exercise, the hash for a block is generated with the data comprising the block number, the timestamp, and the previous hash value, along with the data for the transaction. So each block references the previous one, forming the chain. So let's have a look at the code. This was our source code at the end of the last video. This source code is used to compile both applications. The definition of the monitor constant here at the top of the source code is used as a switch to define whether the application will compile as the monitor application or the actual processing application. Today, all the changes we're going to be making are to the processing application, the blockchain demo. We'll be making no changes to the monitor application. So in order to support this new blockchain transaction source code, we're going to add a new include file. And this is going to be called blockchain transactions. As this source code will not need to be included into the monitor application, I've wrapped this in the definition check for the monitor constant. So this is our new include file. So within this include file, we're going to define the content of the blocks. Part of this content is going to include 2 hash strings, and we're going to include 3 include libraries which we've used before for file hashes. In this case, we're just going to be hashing a string. Having added these 3 include files, our next task is to define the structure of the block itself. We're going to use a user-defined type for this. As described earlier, one of the things we need to keep track of is the block number. This is the unique index of the block to give us an idea of what order they were created in. I'm going to create this block number as a 10-character string. This will allow us to keep track of up to 2,000 million blocks, which is more than enough for what we need to do. The next element within our user-defined type is going to be a timestamp. This is the date and time down to the millisecond when the block was actually created. Next, we need to keep track of the actual transaction data itself. I'm allowing 255 characters for the transaction data. The next element within our block is going to be the previous hash number. This links the block to the block that preceded it. And we are allowing 32 characters for this hash. To complete the user-defined type, I'm putting a buffer of 1 character in to separate the 2 hashes, and the final element is a hash string. This is a hash of all the elements of the block that preceded this, and this will be passed on to the next block in the chain to populate the previous hash value. Now that we've defined the structure of each of the blocks, we next have to think about how we're actually going to store this information inside the application. We could create an array of user-defined types, and every time we did a new transaction, we could add another record to that array. We would also need to create something to allow us to search out information within that array. However, there's a construct within PowerBasic that will do a great many of these things for you, and that's called a power collection. We've created videos on the power collections before, but we'll go over some of these again just to let you know what's happening. So I will now create a global variable as a power collection, and we'll call that global variable blockchain. So we now go back to the main part of the code. I'm going to add two new string constants in here, one called blockchain file, which will be the name of the file we will be saving the blockchain to. Once the application on one of the processing nodes completes, I want it to save its current blockchain out to a file so we can look at it. This file can also be used when the application runs again to load the existing blockchain back into the application. And the second constant is closing balance. As we saw in the last video, each processing node starts off with an asset count of 100. And during the run of the application, it will attempt to transact these to other nodes. So although it starts off with 100, this number may go down or up, depending whether it's actually bought or sold assets. So once the application completes, the value left in the closing balance will be dumped out to this closing balance text file. So now that we've defined the content of each of the blocks, how are we going to actually start this up? Let's look at the pbMain function. The pbMain function is in two parts. The first part of the pbMain function is where everything is prepared. We prepare the global array, the number of assets, and then in the second part we create the monitor thread, which does the majority of the work within the application. There's one additional piece of prep we need to do at the beginning. This is to prepare the blockchain. As we only want this running on the application itself and not on the monitor, we're going to have to wrap this in a conditional compilation. We're using the let command to set the blockchain to the class of power collection. As the plan is to save the blockchain to disk after an application has completed, our first task when the application runs is to check to see if there is an existing blockchain file that needs to be loaded into the collection. So we can test for the existence of this file. If this file does exist, we'll need to use a function to pull that information into the blockchain collection. If this file does not exist, then we can initialize the blockchain. So we have two new functions we need to create, one to initialize a blockchain, which will create the Genesis block, and one to load the blockchain from the file. And these new functions are going to be in our blockchain transactions include file. So let's first of all create the initialize blockchain function and explain how our block is initially created. So first of all, we will create a local variable as a user-defined type. This is using the uBlock type we created earlier. As this is the Genesis block, its block number will be 0. And we're setting an arbitrary timestamp for this block. This timestamp and the block number will be the same for all blocks, which are the Genesis block. Our transaction data in this case is just a simple string saying Genesis block. Doesn't really matter what the transaction data on this block is, this is just a place to begin. This is the foundation of our blockchain. And the previous hash is an arbitrary value just to give us somewhere to begin. The final element within this user-defined type is going to be our hash value, which is a hash value of the block number, the timestamp, the transactional data, and the previous hash. So I'm going to create another function whose job it will be to return the hash for this particular block. And we can make use of this function later when we're generating the transactional blocks themselves. We'll come back to this function in a moment. But let's work on the assumption that we have now populated all the fields within our user-defined type. Our next task is to add this to the power collection. And we're going to set up a wide string. This will be our unique key on the collection itself. And I'm going to use the hash value of the block itself as the key. Having defined the key, we can now use the power collection to add a new value to our collection. And we're using the add method. This takes two parameters. We're giving it the key itself and the user-defined type, which we're defining as a string. We can test to see whether this operational has been successful or not. If the object result equals SOK, then the operation has been successful and we can say that the Genesis key has now been stored in the collection, and we can return true to the function. If for some reason we have been unable to add this value, then it will return false. One of the reasons you may not be able to add a value is if the value you're adding, the key, already exists within the collection. So now that we've completed this function, let's double back and create the return hash for block function. In order to do this, I'm going to go into one of the include files, the pb file hash. In this include file, there's already a function called getSHA. This returns the hash value of a file. It loads the file into a string and then returns the value as a hash of that string. This is very similar to what we want to do. So I've created a cut down version of that function which takes in the string to be hashed. It then calls the inbuilt function to calculate the SHA, giving it the string and the user-defined type. It will then return from this function the value in a string. This easily allows us to calculate the hash value of any string passed in. So that is us completed the initialization of the Genesis block. So the other function we referenced earlier was the load blockchain from file. We need to create this one as well. So if we go back to the blockchain transactions include file, and we will create the new function within there. We're passing in a single parameter, which is the path and the name of the file which contains our blockchain data. So we're creating some local variables to define the handle of the file, the string of a blockchain, the user-defined type we're going to put the data into, and the key, which is the key for the collection. So, encapsulated in a try-catch block, we're going to attempt to open the file. And while that file is open and still giving us data, we will load each record within that file into the blockchain variable. And having loaded that value into that string, we can quite easily populate the user-defined type in a single line of code by using the typeset command. So now that we have our block, we now have to place this block within the collection. And we do this just the way we did it earlier. We're using the add method to add to the blockchain, using the key, which is the hash of the block, and the user-defined type as the second parameter. And we can test to see whether this worked or not. And we can quite simply close off our function at that point. As the data within this text file has come from a collection, it's highly unlikely that we'll have duplicates in there. But if you think this is necessary, please feel free to add in your error handling. The next new function we have to create is the one that returns the hash for the block. We will create this also within our blockchain transactions include file. This is going to be a very simple function. It takes in a single parameter as the user-defined type. And it's going to call the getString by adding together the block number, the timestamp, the transaction data, and the previous hash. I've delimited each of these using the pipe character, so it's basically getting one big long string and returning the hash value for that. So with that in place, our application compiles quite happily. So now we've created the code to create the Genesis block. We've also created the code so that once the application restarts, it will test to see whether there's a text file containing the blockchain data. When the application terminates, we'll need to create that text file by dumping out everything in the blockchain to it. So at the end of the code, where we run the deactivate this node function, we'll want to tack on two functions. One to save the blockchain to the file, and one to save the closing balance. So, two new functions we will need to create. Each of these functions takes a single parameter, which is the path and the name of the file to create. So we will create the save blockchain to file first within our blockchain transactions include file. This one is very similar to the load function. We're creating three local variables, one to be the file handle, a variant to contain the data, and the user-defined type block itself. Encapsulated within a try-catch block, we're attempting to open the file for output. And for each vdata in the blockchain, we're populating the user-defined type. We're using the typeset command to set the value of the user-defined type block using the variant $command. This quite easily pulls the information out of blockchain and puts it into the user-defined type. We can then print that user-defined type straight out to our file, as everything in that block is a string. We then use the next command to look round until we run out of blocks in the blockchain. And at the end, we just close the file off. And the second function we have to create is the save closing balance. We will create that in the main file itself. This is taking its single parameter, being the path and the name to the file, opening the file, printing out the value, and then closing the file again. This file is only going to be used so we can check the data. And again, everything compiles quite happily. So we can now load up a previous blockchain file. We can dump out a blockchain file at the end of processing, and we can set up and prepare our Genesis block. What's left to do is to actually save each transaction as they happen into the blockchain. So we can build up this blockchain as a series of transactions. Within the monitor thread function is the place we'll want to put this code. As the transaction happens between two processing nodes, one processing node makes a request to transfer an asset to another node. When the second node confirms the transaction back to the originator of the transaction, it can then subtract the value of the assets from its current list. At that point, we want to add the transaction onto the blockchain. So we will see in here we're looking at the section of the code which handles confirmations. So after the number of assets has been removed from our asset list, we want to add it to the blockchain. So we will create a new function to add to the blockchain. All the details of the data of the transaction are held in the str message variable. So we will create this new function within our blockchain transactions include file. So we're taking in this single parameter, which is the data we're going to put into the block. We will need some local variables. A user-defined type to hold the block itself, a string to hold the last block number, and another string to hold the value of the previous hash. And then we're going to use a variant to hold the data coming out of the current collection. First, we need to get the details of the last transaction in our blockchain. So we can use the last method to move to the very end of the blockchain. We can then populate the vData with the block, which is the very last block, using blockchain previous. Assuming that is OK, we can now populate the user-defined type with the data from that variable. Again, testing to make sure that the object result is OK. Then using the type set, as we have done before, to populate the data within the user-defined type. Now we can pick up the hash number of that previous block. And we can also populate the block number of the previous block. Now we can prepare our new block. The block number of our new block is equal to the value of the last block plus 1. We want to set a timestamp, so I'm going to create a little function to pull back the current date and time, down to the nearest millisecond. We'll create that new function in a moment. We know the transaction data because that came in as our parameter, str message. And the previous hash is going to be the hash we have just pulled back from the previous block. Having populated this block, there's one element of the block we now need to populate, and that's the hash giving all the data we've just put into the block. And we can use the function we created earlier to return the hash for the block. So now our block is complete, we can look to add it to the blockchain collection. Again, using the key of the hash number itself. And just as we did before, we're going to use blockchain add to add our block to the blockchain. Using the power collection in this way saves you a great deal of coding. So we now have to double back and create this new function to get us a timestamp. This little function takes no parameters and returns a string. There are a number of ways of actually generating the current time, but one of the easiest is to use the inbuilt PowerTime class. We create a variable as a PowerTime variable, and we set its class to PowerTime. We can now use the now method to pull up the current date and time. We now want to return the date and then the time, and we can use the inbuilt properties of the PowerTime class to do that in a single line of code. This will return the date string, a space, and then the time. So our application compiles quite cleanly, so we haven't missed anything. So as we did in our last video, we're going to have 4 processing nodes, Odroid 1, 2, 3 and 4. And we'll be using this computer, Octal002, as the monitor application. I've created a little batch file to copy our new executable, the blockchain demo exe, onto each of these machines. And that's the new executable now copied onto each of the processing nodes. So if we look at one of the shared areas where the executable has been copied to, we'll see that only the executable sits in there. There is no blockchain file. So the application, when we start it, will be starting from scratch. It should create a Genesis block and then start to do transactions with the other nodes. And once we terminate the processing application on each node, the blockchain data should be dumped out to a file which we can have a look at. So let's first of all run the monitoring application on this computer. And that's it running. So we will now start the process on each of the processing nodes. So as we can see from our monitor application, all 4 nodes are now active. So we just have to wait for these nodes to prepare themselves and start to do transactions. And there are our transactions just starting. We'll give it a moment or two for a few more transactions to come in, and then we will terminate the applications running on each of the nodes so we can actually check to see whether the blockchain has been created and saved out to file. So we have 2 confirmations, we'll wait for 1 or 2 more, and then we can have a look at those files. Right, I think we have enough data there. We'll now terminate the application running on our processing nodes. If we have a look at Odroid number 1, we have the 2 new files, the closing balance file, which currently sits at 98. If we have a look at the demo blockchain file, we'll see that we have the Genesis block as block 0, and we have 3 additional blocks, 1, 2 and 3, each of which has the time and date on it down to the nearest millisecond. And we have the transactions itself. Odroid number 4 is confirming a transaction done with Odroid number 1. And there were 3 assets involved. And if we move all the way to the right hand side of the file, we will see the 2 sets of hash values. The line at the very top has the initial hash value of the Genesis block, and the beginning of the next line has the hash of the previous value. And this works down all the way down the file. So we can see we have successfully created a blockchain, each block referencing the block that preceded it. However, there's something missing from our blockchain. There are 2 more pieces of functionality we'll need to build into this application in order to allow the blockchain to work correctly. If we look at the blockchain of one of the other computers, we will see that it has a slightly different blockchain. Ideally, our blockchain should be identical regardless of which machine we look at. But as we're only trapping the information to add to our blockchain on a confirmation event, we're missing out on the blockchain transactions that happen between 2 other nodes. If Odroid 1 is doing a transaction, it will only have confirmations where it was involved. So we need to perform synchronization of the blockchain, so that every node in the system has a blockchain which is complete of all transactions. The second thing that needs to get done is to handle the event when a processing node comes late. We started all the processing nodes at the same time. If, for example, we started 3 of the processing nodes, waited a few minutes until transactions had already begun, and then added the 4th node. The 4th node would have no record of the preceding transactions, and would work on the assumption that it was starting from 0 again. So this also leads into the synchronization of the blockchain. However, we'll cover that in the next video. That's it for today. Thank you for watching.